Intro to static loading. Okay, so what is static loading? When there's repeated stress, you observe that materials fail, and they fail faster or earlier than they would fail with static loads. And fatigue loads are important because most of the things we see today are subject to fatigue loads. So before 19th century, all designs were based on static loads. We did not have too many things moving fast. But since the 19th century, after the 19th century, with the advent of steam engines, we had to design based on fatigue loads. Because when you have something which is moving several times per second, you have these loads which are fluctuating, and fluctuating failures are much different from static failures. So the key thing about fatigue loads is that key things. One is failure stress is much lower than yield strength. So if the stress at failure is sigma, if you when it's loaded with a static load, a constant force or constant stress, then if you now change the stress to be a pulsating stress, then the failure will occur much before the yield strength. That's one thing. Second thing is we are interested in finding finding here empirically or using some theory, one load at which, or let's say stress at which failure occurs. Fatigue failure occurs. And then the other thing we're interested in is the number of cycles to failure. Okay, the stress at which failure occurs is usually called it the endurance strength, SE. One is SE, endurance strength, and the cycles will use the letter capital N, cycles to failure. I'll just put cycles in because we can just use N for cycles. Okay, so we are interested in knowing the endurance strength and what are the number of cycles to which something will fail. Okay, so that gets us to different ways of predicting the life of a material when subjected to the cyclic loads. So there are three methods. Fatigue life methods. So the goal here is to predict cycles or N to failure. We have the strain life method. Okay, so the question is, why do things fail in fatigue? Well, it turns out that when things fail in fatigue, there's usually a crack in the material when you subject to stress. So the strain life method uses this crack nucleation, or that's the beginning, to predict n. The second one is the linear elastic fracture method, which uses the crack propagation to predict n. Okay, so we've not really talked about fracture mechanics, but fracture mechanics is a field which understands how things fracture or break. And there are theories behind it, and we've not really done that. So we'll not really touch upon fracture. The third one, which is probably the one which we'll talk about in this course, entirely the whole of this chapter is on using this third method, is called the stress life method. Okay, so the other two ones are sort of dependent on the microstructure. You sort of look at the microstructure and then you make predictions. And we never really get into microstructure in this course. So what the stress life method does is that it just says it takes a material, it loads it to failure, and then generates some kind of a plot, right? Just like we had the yield, the stress strain plot for ductile material or brittle material in order to predict failure. So this is a empirical test which just takes experimental data to figure out when failure would occur, or what is the n for a particular material. So these are empirical tests based on testing a specimen in lab conditions. Okay, now this one is the least accurate. Okay, the least accurate term is a very relative term, but it's least accurate compared to 1 and 2. However, it's the most, so it's the easiest one and most used. So for design purposes, this method suffices. Yeah, and so what we'll do now is we will only study this method. We look into number 3. Okay, we'll ignore the other ones. If you want to learn about the other ones and you're interested in solid mechanics, there are courses at the elective level and beyond, which teach you about fraction mechanics, and that's where you learn about those things. Okay, so let's move on to the stress life method. So 607 stress and the SN diagram. Okay, here S is the strength and N is the cycles. Again, that will become clear when we talk more. So as I said, this method is based on laboratory tests, right? So you need to devise a experimental protocol where you'll have a test specimen, like you had the uniaxial strength test. You'll have a loading condition, and once you have the loading conditions, you'll observe how things fail, and you'll make a plot. In this case, the SN plot. And from the SN plot for different materials, you make some hypothesis about this is how things behave, and then we'll have those points on this curve and sort of model it. And once you have the model, we can use that model to predict failure for that material under other conditions, under other ways in which it is used to design other things. So let's do a few things about the different conditions under which this test is done. So first is the loading. How do you load this? Well, what you do is you have what is known as reverse loading. And I could draw it, but let me just put it from my screenshot. Okay, so you can see that this is the zero stress, this is the max stress, and this is the min stress. So you see that it's when you load the material, the stress goes between positive value and negative value in a cyclic way. You could have whatever you want. For sigma, you could. So this is stress. You could, for example, write it as sigma A sine omega t, where omega is some frequency. Right, and then t is time. And sigma is the amplitude. So if you keep cycling this with a certain frequency, you will have those many cycles. So the cycles are basically hidden in here, right? This is one cycle, peak to peak. So clearly, if you increase frequency, then you will have these closer together. It means that you can do many more tests if you increase the frequency. Of course, there are limitations to how fast you can apply the load, right? Those are generally limited by the test setup and the money you have in buying a good setup, which will do a fast loading. So that's the number one thing. The second thing we want to understand is what is the loading condition under which, or sorry, the test specimen we need to use for this. So the second thing is test specimen. Okay, so this test specimen is very similar to the one we saw for uniaxial test. However, it is used in loading. So let me pull that up. Okay, so the test specimen looks similar, except that the loads are not axial here. The loads are, there are four loads. There's capital F in the direction shown, and that's reversed, and then same direction as this F, and then up. So what this does is, if you draw the shear force diagram, so let's draw the shear force diagram. Okay, you'll see that the shear stress is positive, goes to 0. Just draw it in red. So it's positive and it goes 0 here. And it stays 0 because those forces cancel the effect of each other, and then goes negative and 0. So positive, negative, this is capital F. That's going to be minus F. Okay, so that's mildly interesting. What's more interesting is the bending moment diagram. So if you draw the bending moment diagram, this is V, this is M. It'll actually have this, it will be something like this. Your const, it'll be a ramp, and it will ramp down. And it'll actually be a constant in this region. The height of this is F times A, where A is shown here. So the key thing to note is that the part we're interested in, the part which will fail, right? The part which will fail is basically this neck. It's this part which will fail. So this part of the specimen is subjected to a constant load, or a constant moment. Okay, so you can recollect that sigma in, if this is the x direction, then sigma x is my divided by I. M is F times A, y divided by I. So y I f a, or rather, let me just do it this way. So sigma x is that. So sigma. Okay, so let's say that that's the. So the neutral axis is here. Let's say this is d, the max distance on the smallest part of the beam, and then you have sigma x equals f a t divided by I. Okay, so since the moment of inertia I is constant, the d is constant, a is also constant, so sigma is proportional to f. Now my goal is to have a loading which will be sinusoid, right? It will be sigma, something like sigma sine omega t. The easiest way I can do that is to ensure that the force F is some kind of a sinusoid. So what I can do is, so I'll just put F equals some amplitude times sine omega t, and that will make sigma x equals F0 sine omega t times a d divided by I, and you can rewrite this as F0 a t divided by I. I clubbed all the non-time terms together, and then I have sine omega t. Okay, so let's assume that this is sigma a, which is a constant. And so we have now recovered a stress, which is sigma a sine omega t. So we are able to generate a sinusoid loading by simply changing f to be a sinusoid. So that's the test specimen, how the loading is done. Now the final step is the actual experimental protocol. This is how it goes. Let me just do it on a new page. So third experiment. Okay, so we have sigma equals sigma o sine omega t. So the first step is to choose sigma o, okay, and say that this is, let's say this is S, okay, strength. Okay, because I'm going to eventually make a plot of strength versus the cycles. Okay, then to choose a strength, choose a sigma omega. Omega is something which is determined by the testing apparatus, right? You cannot do faster frequency because it might be a limitation there. So this would be based on experimental device. Okay, so then keep increasing the cycles. So you keep loading it. So you 1, 2, 3, 4, 100, 200, 300, thousands, a million, and so on. So you do it till it fails. So then see, note the strength, or note the stress sigma o, which is now S, at and n, at which the material fails, specimen fails. Repeat A, B, C for a new stress. Okay, so we've done this test. What comes out of this test, and this is a very time-consuming process. Think of it this way. for each stress, you need to go over several thousand, or in this case, sometimes millions of cycles. And once it breaks, you take a new specimen, you run the test again, and since the strength now is increased, it'll probably sustain more cycles till it fails. So what comes out of this is a plot, the SN plot, which I'm going to pull up from my notes. Okay, so the final step which I should have done there is so make a plot S or sigma versus n. So on the y-axis, we have the strength or sigma, right? And this is the stress at which the material fails. And on the x-axis, the cycle. So for example, for a particular material, at this point, at this stress, when you choose a stress of this value, whatever it's on the y-axis, it fails at about 5 cycles. And then as you see, as you keep increasing this, keep decreasing the strength, it can sustain more and more cycles till it fails. And so the line here, so these are experimental data. Okay, this line which you see here is sort of the least square fit to this data. This plot is made on a log scale, which is if this is the y-axis, it's kind of miswritten here. So y is actually log of s, and x is actually log of n. So when you make it on a log scale, it looks nice. If you do it some other way, then you can't really plot like this, because clearly what is 10? This is 1. This is 10. This is 100. You can't have 1, 10, 100 with equal spacing. But when you do the log, you can see it. So it's really, in this plot, it should be 0, 1, 2, 3, 4, which is shown, but it's not shown the right way here in the book. Okay, so what we notice here is this is what is known as the endurance limit. Or fatigue limit. Okay, why it's called the endurance limit? Well, it turns out that when the material has this fatigue limit or the strength limit, you see that this curve is almost parallel to the x-axis, which means that it can sustain infinitely many cycles without failing, right? So here the life is infinity. So as long as the stress is equal or below the stress, this material will never fail. So when I say the stress, it means the external stress. Say it again. No. This all is in the elastic range. We are all assuming that, yeah, right. So this all in the elastic range. The theory we are looking at, stress life theory, is for the elastic range, and the other theories are more for the plastic range. But you're right, this is all in the elastic range. Okay, so that's one thing. The other thing you want to see here is that there are what they classify low cycles and high cycles. Anything below 1,000, right, 1,000 is considered low number of cycles, and anything above 1,000 is considered high number of cycles. Okay, this terminology comes because of the fact that you notice that exactly at 1,000 cycles, and for most materials, the curve starts dipping dipping quite fast. Okay, and so they just use 1,000 to separate low from high. So it just shows you that as the stress, the external stress is high, the material will fail for a fewer number of cycles. And then as the stress goes down, the life increases, which means that it takes more and more number of cycles to break the material. This Sn curve has some names, and I just put it down. So historical Sn curve is called Sn curve, of course. It's called I believe it's a German name, and stress life curve. Okay, so what we're going to do is, we know this is how materials fail, and we're going to use this curve in order to make predictions about different materials. Okay, so from this comes what is known as the idealized Sn curve, and I'm going to show that to you. So this line which you saw, which is the least square fit, can be used to make predictions. So this is an idealized Sn curve. Okay, so there are some approximations here, right? So you have this king, so it's sort of 3 lines. There is this line, which is in the low cycle fatigue. There is this line, which is a slightly bigger slope in the high cycle fatigue, and then there's this line which is parallel to the x-axis. Okay, so what we need to do is, we need to write the equations for these lines. So once you have the equations for these lines, we can then make predictions. For example, can we predict at this strength? So if you're given this curve, and if this is the loading on the material, can we predict the number of cycles to failure? First, we'll have to identify this strength S is in this region, right? And then we need to identify this line. If you know the curve, which this is how it the model for the curve is, and we can predict the number of cycles to failure. That will be our goal. Our goal is to model these lines. So these are 3 lines, as I said, 1, 2, and 3. It turns out that you don't really require too much information to model them. It's kind of simple. When you notice that SUT is the ultimate strength, which we typically know for different materials. And that's something we do in the actual loading case. We'll assume that this is this point where it changes from low cycle to high cycle fatigue is a fraction of the ultimate strength. So F is again an empirical quantity, which is typically taken to be 0.8 or 0.9. So how did this come? Well, it comes from looking at the data and making a prediction on where this curve will start dipping faster. The other thing we want to know is this point, right? If you want to draw a line, then we need to know 2 points. So there's the endurance strength, which is an unknown. And then there is the number of cycles, which is known. So the coordinates of this point are 10 raised to 6. This is a cycle, and then the endurance strength. And this point is 10 raised to 3, which is the cycles, so the x-axis, and then F times SUT. So given that you know these points, it's very easy to draw a line here, right? Because you know the coordinates of this point, it's x is 0, y is SUT. So this line is known because you know 2 points. You know this line because you know 2 points. And the third line is just parallel to the x-axis. So the goal next is to model, well, we only model this part. This one can also be found, but we'll only model this part because that's where most of the interesting things go on, right? We don't want to limit ourselves to a very low number of cycles. We typically want applications to run for more than 1,000 cycles. So it's this curve which people are sort of obsessed in modeling. And of course, predicting this point so that you know that beyond that point, it's going to have infinite cycles. Okay, so let me make some notes here. And in region 1, we have the low cycle fatigue. In region 2, we have the high cycle fatigue. And then the third region is infinite life. So this is the region which is the most interesting. We need to model this part. Okay, so when I say model this part, we need to know SE, we need to know F, and that's pretty much it. So we know F, we know this point, and if you know SE, we know that point. Okay, so what I'm going to give you is basically, these are just experimentally determined values for SE and F. So I said 0.8 to 0.9, it's a good ballpark, but there are people who have done a better fit to this line and figured out F and SE based on empirical data. So this is the curves which describe these 2 points. So SE, F are found empirically. The value for steel. Okay, so different materials have different values. For steel, which is at one point of time, it was the main material being used for many of these things. Clearly, you can't use this for machinery like which is going to move, but for railways, it's okay to use steel, or even something which is on the land, which is not going to move. Now I'm going to write SE prime and not SE, and I'll say why. I'll tell you why I write SE prime in a bit. But SE prime is 0.5 SUT, and it's 100 kpsi. So this is the IPS unit. So if you are looking at the value for SE in IPS unit, then these are the formulas you use. So if it is less than 200 kpsi, then you need to use the first one. If it is greater than 200 kpsi, then you use second one. If you want to find SE in SI units, you can actually convert the above formulas, or you can just read out of this table. So 700 MPa, this is when SUT is less than, it should probably be greater than 1400 MPa, if SUT is greater than. Okay, so the difference is that the units, so this is in the IPS units, this is in the SI units. So you can use the formula you are expected to use depending on the problem. Now, why did I write SE prime and not SE? So SE is endurance for the test specimen. So clearly, when you have the test specimen, you observe it, you get this curves. SE, on the other hand, is for the endurance for the actual machine element. So when you take that piece of steel and you put it in the machine element, its endurance is going to be different, and it's going to be different because of various things like imperfections. There would be notches, there would be stress concentration, and so on. And so we just distinguish those two. So we'll sort of make a correction to the SE factor later on, and it will come later on. So this is due to SE. So SE prime is not equal to SE as the steel in the machine might have imperfections. Okay, this will be addressed a bit later. So I'll show you how SC prime is related to SC in a bit later. Okay, so that's about SC. What about F? So here are the formulas for F. So 0.8 and 0.9 are good ballparks, but if you want to be really accurate, then these formulas are to be used. 2.8 10 raised to negative 3 times SUT plus 6.9 10 raised to negative 6 SUT square. This is if SUT is within 70 and 200 kpsi. So this is the IPS unit. And if you want to go SI, then it's 1.06 minus 4.1 10 raised to negative 4 SUT plus 1.5 10 raised to negative 7 SUT square. And this is if stress is between 500 and 1400 MPa. So the reason why it's capped off at 1400 is because 1400 MPa is actually the ultimate strength of steel. And so you won't really have a stress of beyond 14 MPa. Or good, so sometimes F is assumed to be 0.8 or 0.9. So sometimes just assume 0.8, 0.9, but if you actually put the values in this formula for the SUT, you'll actually see that it's actually 0.8 and 0.9 corresponding to those two pounds. This is SI and this is IPS. Okay, so okay, so what I'm going to do next is, so we found this formula, we found SE, we found F totally from experiments, but now we have the second goal is to find this curve, right? This curve is modeled as SF equals A times N raised to B. Okay, so it seems a little bit strange. So why is that curve SF equals A times N raised to B? It's because of this. So I said the x-axis, so the y-axis is log of S, and the x-axis is log of N. And we know that this line is a straight line in the log scale. So we can write equation as y equals mx plus c. That's the equation of a straight line, but we can sub in the value for y. It's log s equals m log n plus c. Now there's a rule in logarithms, which is you can write m log n as log n raised to m, right? That's same as m log n. And then if you and you can find a logarithm which so a log of something gives c. So you can write this as, what we'll do here is instead of this, let's assume that m is b, okay, and b is just another constant just like m, and then we'll find the sort of the anti-log of c to get to relate c with this another constant a. So how do you get a? Well, you take the anti-log of both sides and you get anti-log of c is a. Okay, so don't worry too much about the anti-log. You don't have to remember how to find anti-log and things like that. I'm just trying to replace one constant with another one so that it matches this equation. So if you do that, you get log s equals log n raised to m, but m is b, and then c is log a, right? Now there's a rule in logarithm which is you have log a plus log b is log a times b. That's the rule. So I'm just going to combine them. Log a times n raised to b is log s. And now what you can do is you can see that if you get eliminate logs, or you take the anti-log of both sides, you end up with s equals n raised to b. And that is the formula they have over here. It's not very obvious when we write it down that way, but it's derived in this fashion. Okay, so hopefully I've convinced you that's the equation, and that equation is actually not on the log scale. That's the equation in the scale where you have x-axis as n and y-axis as s, and not log s and log n. Okay, so our goal, so given that equation, I need to find a and b. Once I find a and b, perfect, I found that equation. So let's get to that. Okay, so our goal is find the constants in the equation s equals a times n raised to b. Okay, so since there are two constants, all we need is two conditions, right, to find this constant. So we know that 2 points on this curve are this point. So since this is the curve, one is 10,000 comma f sut, another one is 10 raised to 6 comma se. So I'm just going to use that fact to find those constants. Okay, so this curve passes through 10,000 and comma fsut, and also through 10 raised to 6 se. So I can just sub in the values. So I have fsut equals a times 1,000. So 1,000 times raised to b, so 10 raised to 3b, and then se equals a 10 raised to 6. Okay, so I need to find those constants. What I can do here is the following. I can take the ratio of 1:2. If I do that, then a's will get eliminated, and I'll be left with 10 raised to, you know what, let me just do 2 divided by 1. It's easier. So I'm just going to flip this se. So we'll have 10 raised to 6b, 10 raised to 3b equals 10 raised to 3b. So now if I want to find b, I need to take the log of both sides. And so b is 1/3 log se Okay, I will just do the second part. Give me maybe a minute more than the usual ending time, but I'll finish this finding a. Okay, now what we'll do is take log 10. So we take log to the base of 10 of one of them, 1 or 2. You can choose any. Let's take 2. It seems much simpler. So log of 2. So we have log 10. So SE base 10 equals now log 10a plus 6b log 10, 10. So 10 to the base 10, and 10 to the base 10 is going to be 1. That's the rule for logarithms. And now I can sub in the value for b, right? 6b. We can sub in the value for b. It comes out to be 2 log c. Okay, I'm almost done. Let me just write the formula. So what needs to be done now is you have to use the same rules. This is by the way 10. You got to use the same rules, combine these together using the law of logarithms, and then take the antilog of the whole thing, and you end up with this expression for a. So a is f times fut square divided by c. Okay, so that's the value for a, and we found value for b, and so we've modeled that curve and then make a predictions. How does the prediction done? Well, if we are, so now we know a and b. Now what we can do is the stress, the equation is SF equals A n raised to B, where A, B are computed. So there could be two questions. One is you could be asked, given a strength SF, predict n, or given the number of cycles, predict SF. So you just have to take the right kind of inverse, right? So let's say that if you're given predict n, so what you'll do here is you will divide by A. So I'm just trying to find n now from this equation. So I'll divide it by A, and then I take 1 divided by B, and that will give me n. And it also works the other way. That is, if you're given n, you can find SF, which is this formula. So given n, you can find SF, and vice versa from the other formula. So let's solve a problem based on what we have talked so far about modeling the fatigue diagram using this Sn curve. So here is okay, let's focus on the question first. So given a 1050 HR steel, this type of steel, estimate the endurance limit at 10 raised to 6 cycles. Okay, so what's 10 raised to 6 cycles? That's the cycles at which you find that, let's go back. It's the cycles at which you have the infinite life, right? So to find the endurance limit, the endurance strength of a polished rotating beam specimens corresponding 10 raised to 4 cycles to failure, and then expected life of a polished rotating beam specimen under completely reversed load stress of 55 kPSI. Okay, so what we are asked is this. So let's just put that down first. This one is asking us to find the endurance limit, and this is for the specimen. So I'm going to put a apostrophe there to distinguish from the machine element, and we'll be talking about SC without the prime a little bit later. Then we need to find the endurance strength of a specimen corresponding to 10 raised to 4 cycles. So if we can model this equation, then given n, we need to predict SF. And then the last question asks you to predict the life, which is n, given the stress. So this equation, same equation holds true, but now we are given SF, predict n. Okay, so let's think of how we can solve for these things. So what about the endurance limit? Do we know anything about the endurance limit? How is it related to the material properties? And this is something which comes from empirical data. I think I have it right here. Right? This is just saying that if you know the ultimate strength, then you can predict the endurance limit. Now this is for IPS, and the bottom formula is for SI. So in this case, since we are interested in IPS, I'm going to take this formula. Copy. Let's do it on a new page. So the question is, can we compute SC prime? Well, we need to know the ultimate strength, right? So how do we do it? Well, if we know the material, it's H050 HR steel. There is a table in the book, which I copy pasted here, which tells us how to find the ultimate strength, because it's tabulated here. So H050 1050 HR steel. So here's HR, and that's 1050. So HR, and then we want the strength in. So we need the ultimate strength in kpsi. That's the number we're after. This is SUT. And this is the yield strength. We're not interested in the yield strength. So 90 is the value. So I'll use that. SUT equals 90 kpsi from the table. This is a formula I wrote down earlier, which is based on an empirical fit. And so from these two pieces of information, we can write SE prime is, since it's less than 200 kpsi, we have 0.5 SUT, which is 0.5 times 90. So SE prime equals 45 kpsi. Okay, so part B, we need to model the Sn curve. So for that, we need to fit this expression. We wrote down that A equals FSUT square divided by SE. In this case, SE is SE prime. And then B is 1/3 log the base 10, the ratio of SE divided by F times SUT. Okay, so we have SUT, we have SE prime, we don't have F, the fraction. So F is another empirical fit, which is given, should be here somewhere. So again, here is the fit in kpsi, and that's the fit for SI. So I need the kpsi one, so I'm going to copy this. Yes, so that's a piece of information which is given. So I can find F. It's going to be 1.06 minus 2.8 negative 3. SUT is now 90. 6.9 10 raised to negative 6, 90 squared. So if you sub in the value for SUT, which I wrote down there, you should get 0.86. Okay, so we have F now, and so now we can find A. It's 0.86. SUT is 90, the whole square, divided by SE prime, which is 45. I think that comes out to be 133.1. The units of this is actually the same as units of strength. And then B is 1/3 log to the base 10. So we have SE prime in the numerator, so that's 45. In the denominator, we have F times SUT. So F is 0.86, UT is 90. So B comes out to be negative 0.07. Okay, with that, we are ready to solve part B and C. So the part B asks us to find, so we know A and B, and now we need to predict N. Sorry, given N, we know N is 10 raised to 4, we need to predict SF. So we write SF equals to A, which is 133.1, n raised to b. So n is 10 raised to 4, and b is minus 0.0785. So from that, we can find SF it's 65 kpsi. And finally, for C, we have SF equals, there's a question. What if SUT doesn't fall between 70 and 200? Well, this I believe is for steel, and for steel, the strength only is between, you only see 70 and 200, because beyond 200 you'll have failure. And what happens below 70? I'm blanking on that. But 200 is the max. The min, let me think about this minimum limit, 70, and get back. SF equals A times n raised to b. And so we can solve for n, that it's SF raised to A, 1 raised to b. And so now we are asked to solve for, we're given the strength, so we're given SF, we need to predict n. So n equals 55, and A we know is 133.1. 1 divided by b, which is minus 0.07. Okay, so solving for n, get this comes out to be like 77,500. Okay, what does that mean? It's n is approximately 7.8 times 10 raised to 4 cycles.